it says here that, I'm going to go. This is a nice big room here. We're lucky in that sense, because the next one over, you're kind of crowded in there. But the next one over has a really, really good computer, a brand new one. This thing here, I think, must have been on the Ark with Noah or something, because it is extremely slow, at least when I've been in this room. But maybe it's better now. I don't know. Give me just a bit here to take back what I said. It's not getting better. All right. Let's try this one. Success. Now, can everybody see the right? Row one here is kind of in the semi-dark. You all okay? All right. So what is this? It's blood cells. They're red, so there must be red blood cells. But I mean, what is the whole picture there? What are these contained in? What's this? It's a blood vessel, isn't it? This is probably a small vein or a very small artery. Small arteries are called arterioles. And I know this because I know the diameter of a red blood cell, and I see 3 across and a piece of one right there. And I know that red blood cells aren't very large, so it has to be a very small blood vessel. This is the blood vessel wall. This is an electron photomicrograph. You know, very highly magnified. So we're starting off talking about blood. Now, why do we start with blood? What's the logical reason that we start with blood.
If you don't have blood flow, you die.
Exactly. Exactly. We have to have blood present in sufficient amounts and moving through the body to stay alive, don't we? Okay, so the issue of life resides in the blood. Now, back before physicians of the 18th century, even the 17th century, really understood the physiology of blood, before medieval times when physicians had no real clue about the nature and function of blood, way before that, as many as 3,500 years ago, 3.5 millennia ago, there is a simple sentence in the Bible, in the book of Leviticus, a book written by Moses. It says, the life of the flesh is in the blood. Flesh referring to the body. One simple sentence says it all. That doesn't tell you all the full nature and function of blood, but that's it. The essence of life resides in the blood. Now, can you have enough blood in you and still die? Yeah. Isn't that what happens in a heart attack? A person may have all the blood he or she would normally need, but if the heart isn't pumping that blood, it's of no use. So you have to have blood in sufficient volume, and it has to be moving through the body continuously, because all cells, tissues, and organs of the body are vitally dependent on an adequate blood supply. Now, whenever we take up a new organ system, we always look at the functions of that organ. Now, blood is a tissue, and so let's look at the functions of blood. 3 big categories here: distribution, regulation, and protection. As far as distribution is concerned, the transport of the respiratory gases, oxygen and CO2. This is crucial. It also transports some hormones. It transports the nutrients that we absorb from the process of digestion from the food that we eat. Right. The blood distributes those nutrients to the cells and tissues and organs of the body. It helps to regulate our body temperature. When we are overheated, our blood vessels dilate and the blood moves closer to the surface so that we can lose some of that heat that's in the blood. When we're cold, those vessels constrict and direct blood more to our core organs to support the core organs. The blood helps us to maintain a normal pH. pH has to do with the acidity/alkalinity of the blood. We're going to see that the blood has an important function in that regard. It also helps us to maintain an adequate fluid volume by virtue of the plasma component of blood. It protects us from blood loss because of some things that are present in blood, most notably the platelets. And the white cells, the white blood cells in blood, help us fight off infections of various kinds and other things besides infection. Here are some physical characteristics and volume of blood. Its temperature is about this normally. Blood is thicker than water. Viscosity has to do with the so-called thickness of a solution. so blood is about 5 times more viscous than water. Its pH is on the slightly alkaline side, 7.47 being neutral. There's a range of pH in blood. It's from 7.35 to 7.45. Now this is the pH of blood. The pH inside cells is lower than that, but the pH of circulating blood needs to be within this range right here. When it's not, we get in trouble. The color of blood. If we cut ourselves, what color is the blood?
Red.
It's bright red, isn't it? Right. Now, what gives it the bright red color?
Oxygen.
Oxygen. Well oxygenated blood is bright red. All right. But if you go to have some blood drawn for a lab test at the clinic or the hospital, they draw blood from an artery or a vein? A vein, typically. And what color is that blood? It's dark. It's not bright red, is it? Now, why is venous blood dark and arterial blood red? It has to do with the relative oxygenation, isn't it? Now, does this mean that venous blood, the blood drawn from veins or the blood that's circulating in veins, has no oxygen content? No, it doesn't mean that at all. It actually does still contain oxygen, trust me, it does. It's just that its level of oxygen is lower. Now, why is its level lower? Because blood pumped from the heart through arteries is well oxygenated. And where does that oxygen go? It's going to be used up where? In the cells of tissues and organs of the body, isn't it? And that blood is going to come back to the heart to be freshly reoxygenated, isn't it? So on the way back, it has a lower oxygen content than when it left the heart. And when that same blood gets back to the heart, goes to the lungs, comes back, and is pumped out, it's going to be reoxygenated, freshly oxygenated. All right? In a normal adult male, the volume of blood is around 5 to 6 liters. In most females, it's a little lower than that because, as a rule, females mostly have a lower body mass than males, and so around 4 to 5 liters. Now, if somebody asks you the composition of blood, you should say that the composition of blood is plasma plus and formed elements. Now, why wouldn't we say it's plasma and cells? Early lab, tell me the answer to that. Because platelets are not cells. All right, so just call them formed elements. All right. So, if we took some blood from a vein, like you see right here, put that blood in a tube, and we spun it down in a centrifuge, we would see that things separate out. When it was in the syringe, it just looked like solid red blood, kind of dark, venous blood. But when we spin it down, we're going to see the breaking out of the formed elements from the liquid part of blood, which is plasma. All right, so the heavier things in a centrifuge, centripetally, are going to go toward the bottom of the tube, and the lighter stuff's going to be at the top, isn't it? All right, so what we have at the top here is plasma. Plasma is the liquid component of blood. It's the so-called matrix of the tissue. Now, this black line should extend from here down to here. Don't know why, and I couldn't get it back down there. So it should go down to right there to where you see the buffy coat. All right, so this plasma is a liquid component of blood. Now, this red stuff at the bottom is the erythrocytes, which is the technical name for red blood cells. So, in blood, we have red blood cells, erythrocytes, and white blood cells called leukocytes, and platelets. Those are the formed elements. Well, this red column here is the red blood cells. Where are the white blood cells and the platelets? Where do they layer out? Right there. That's called the buffy coat. And if you have a sizable tube here, you can see the buffy coat when you centrifuge out blood like that. So down here, red blood cells, white blood cells and platelets here, plasma here. Now, on this diagram up here, we say that plasma is 55% of whole blood, and our erythrocytes are 45%. That's an average number. There's a range. Not everybody has exactly this, but it's going to be close to this. It's going to be close to this. There's a range. So again, whole blood is plasma plus formed elements. Now, what's in plasma? What's the consistency of plasma? What constitutes it?
Protein.
Well, we've got some proteins in there. Very important. Proteins.
What about
We've got lots
sugars?
of other stuff in solution there. We've got the respiratory gases, oxygen and carbon dioxide, CO2. We've got electrolytes, which are minerals, mostly inorganic minerals with a charge on them. We'll talk about those later. Hormones, nutrients from the food that we've eaten, and metabolic waste. All that's dissolved in plasma. That's important because, as we're going to see later, the kidneys, in order to get rid of certain metabolic waste, have to be presented with these wastes in solution. That's further on down the line, though. But what's plasma mostly made up of?
Water.
It's water. It's mostly water. Over 90% of it's water. And the formed elements are called that because platelets are not cells. Platelets are fragments of a larger cell in the bone marrow that break off from that larger cell and enter the bloodstream. They're very tiny. They don't have nuclei because they're cytoplasmic fragments of a larger cell. But as we shall see later, they contain many important substances that are crucial for the ability of blood to clot normally. Now, these plasma proteins that are in plasma, where do they come from? Where's the main place that these proteins come from? The liver. That's where most of them come from. Now, there's some other places that we find proteins that circulate in blood. Plasma cells. Later on we'll find out about plasma cells, but these are the cells that make the antibodies. All antibodies are proteins. So, and then some of our endocrine glands that produce our hormones, some of them produce hormones that are proteins. Not all hormones are proteins, but some of them are. Now, these plasma proteins, what types are there? These are the main ones right here. Albumins are the most abundant of them. They make up close to 2/3 of all of them. They are important because they contribute to something called osmotic or oncotic pressure in plasma that I'll take up later. They transport different things in the blood that need to be attached to something like a protein, because some things by themselves, if circulated in the blood, are toxic. For example, iron ions. are toxic. They have to be attached to a protein to detoxify them. Okay. Also, some of these albumins serve as buffers in plasma. We'll be talking about buffers a little later on down the line, but buffers are substances that help to maintain the pH of blood within a normal range. Globulins make up just over a third of them. Immunoglobulins are basically the antibodies. Transport globulins are proteins that have a function like albumin because some things are transported as globulins. For example, iron ions, thyroid hormone, and certain lipids in the body. Have you heard of lipoproteins? Okay. A lipoprotein is a lipid molecule basically that has a skin of protein around it, which makes it soluble in blood. And then we have fibrinogen, which makes up about 4% of all plasma proteins. Fibrinogen is crucial for blood clotting because the final stage in the clotting of blood is the conversion of this soluble protein here to an insoluble fiber network that serves as a dam against which the blood cells mass to stop the leak in the blood vessel. So it's important to have enough fibrinogen.
Can I ask a question about that? What is it that actually causes it to go from soluble to insoluble? Is it when it hits oxygen that does that, or is there something special?
We'll be talking
Okay.
about that.
Thank you.
Okay. Just leave it, because I'm going to cover that next time.
Perfect. Thank you.
That'd be too much of a leap to get into it now.
Okay.
Because it's a little more complicated than that. But it has nothing to do with oxygen.
Okay.
All right. Now, we've been talking about plasma, haven't we? Have you heard of serum? All right. Are they similar? Or are they identical? They're similar. They're not identical. They're not identical. Now, what's the difference between plasma and serum? Huh?
Serum still has the red blood cells.
No. Let's go back and look at this just a moment. This is plasma right here. All right? Now, plasma is a liquid component of blood. Now, the clotting factors that eventually convert fibrinogen to fibrin, the clotting factors are in solution in blood normally. Okay? Now, the blood that's circulating in our bodies now doesn't clot unless there's a problem, right? Now, why doesn't it clot? Because there's certain anticoagulants circulating in blood like heparin now, low levels of heparin, that keep our blood from clotting. But once we trigger the clotting mechanism, those clotting factors come out of solution and are bound up in the clot. In normal blood, those factors are still in solution. And so the liquid component of normal blood is plasma. But if you let blood clot in a tube, we would assume that in this tube right here, let's just assume that we put something in this tube here that kept the blood from clotting. We put something in this tube that kept the blood from clotting. So this is non-clotted blood, centrifuged.
What's plasma?
This is plasma. If we drew this blood and put it in just a plain glass tube, there was nothing in the tube, nothing, empty. We put that blood in that tube and let it sit for a while. what's going to happen to that blood? It's going to clot, isn't it? And you're going to have a mass of red blood cells sinking sort of down toward the bottom, and it's going to be surrounded by a liquid that looks like plasma. It's going to be the same color. It's going to look like plasma, but it's not. That's serum. So, then, what is serum? It's basically plasma without the clotting factors. Because the clotting factors came out of solution and are bound up in the clot, in that mass of clot. That's the difference between plasma and serum. I think that's explained in your notes. All right. When are we through here? Quarter till? Okay. All right. How are these formed elements of blood produced anyway? Well, the fancy technical term for this is hematopoiesis. When do blood cells first appear in the embryo? How early? 3 weeks. By 3 weeks, we have a heart that's pumping blood and blood cells that are circulating in blood vessels. The earliest blood cells are produced in an extraembryonic membrane called the yolk sac, which we will be talking about toward the end of the semester. After that, the liver and the spleen are the main sites of blood cell production until basically through the 5th month. So about the 2nd to the 5th month, liver and spleen are the main sites of blood cell production. After that, the bone marrow takes over. So, after the 5th month. All of these formed elements come from one common stem cell. So whether it's a red blood cell, or whether it's a white blood cell, or whether it's the cell that produces the platelets, they all come from one common stem cell called a hemocytoblast. Here it is, right up here. So, here are all of our white cells that come from this cell. Now, there are 2 main stem cell lines from the common stem cell. There's a myeloid line that produces these ones and this one. And there's a lymphoid line that produces only the lymphocytes. So the easy way to remember this is the lymphoid line produces lymphocytes. All the rest come from the other side. Now, what's not shown on this diagram is the precursors for the red blood cells and the platelets. I'll show you that on another slide, but regardless, they all come from the one common stem cell. When you look at a prepared slide of blood, and you'll be looking at this in lab, you late lab folks, this is basically what you'll be looking at, so I'll wait to the late lab. We've already talked about this in the early lab. But this is showing you formed elements here. This is showing you the red blood cells and some of the white blood cells and some platelets right here. All right, red blood cells, or erythrocytes. Again, these are our red blood cells. Now, the number of red blood cells that we have in an adult human body is somewhere in the neighborhood of 25 trillion. 25 trillion with a T. Their primary role is to transport what we call the respiratory gases, oxygen and CO2. cells of our bodies need oxygen to run the metabolic machinery. CO2 is a byproduct of that process. So we have to send oxygen to the cells, and the CO2 they give up, we have to get rid of via our lungs. Now, when you count the red blood cells, when you do a lab procedure to count red blood cells, you count them in so many millions per cubic millimeter or microliter. That's how you express what you find. And so by counting the red cells, you get an idea of whether a person has a normal red blood cell count or not, whether they're anemic or not. All right? So here are some numbers you need to know. Now, it depends on what lab you're in, what reference you're using, but our text basically uses these numbers, so that's what I'm going to use. All right, so in males, the normal count is 4.7 to 6.1 million per cubic millimeter. In females, 4.2 to 5.4. You count so many million per unit. Now, another way of assessing whether we have adequate numbers of red blood cells is something called the hematocrit. Now, HEM is a prefix that refers to blood. All right, so heme, blood. Crit means judgment, so you're judging the blood. Now we're going to be doing in lab red blood cell counts, total red blood cell counts. We'll be doing this. We'll also in a lab be doing this. This is a little more complicated way of getting at the same number or the same result as this. This is simpler. But basically, the hematocrit is sort of like I showed you in the composition of blood. Blood in the tube, we spun it down in the centrifuge, the red blood cells went to the bottom. And so basically, when you do a hematocrit, you look at the total height of the column from the bottom of the red cells to the top of the plasma, and then how much of that total column is taken up by the red cells. It's just a percentage.
That's cool.
It's so simple. All right, it's just a percentage. And so you read hematocrit as percents. All right? So in a normal adult males, it's 47% average. The range is 42 to 42 to 52. Females a little lower. The range is 37 to 47. But you'll be doing these tests in lab. Now, what about the structure of a red blood cell? If we go back and look here, you see that not all of these red cells look the same, do they? Some look solid, some look like they have a hole in the middle. Why is that? Because red blood cells are basically shaped like a biconcave disc. They're fatter around the edge, thinner in the middle. The average diameter of a red cell is about 7.5 microns. That is very small. So they're a biconcave disc, and because of their unique structure like this as a biconcave disc, they have the ability to bend and flex and also stack one on the other. That's very important because it's possible for a red blood cell that's 7 to 8 microns in diameter to go through tiny capillaries that are as small as 4 millimeters or half their diameter because they can squeeze and bend and flex and get through them. That's very important. Now notice that red blood cells in the immature state, when they're in the red bone marrow, when they're being formed from that common precursor cell, the hemocytoblast, they go through a series of stages. During those formative stages, they have nuclei. That's essential because if they didn't have nuclei, they couldn't be making the hemoglobin that they're chock full of when they come out of the bone marrow into the circulating blood. All right? However, in the mature state, most of the time when they come out of the bone marrow into circulating blood, they have lost their nucleus. So they're packed full of hemoglobin. Hemoglobin is the protein that carries the oxygen molecules in blood. So this is why when you look at a peripheral blood smear, the red blood cells will not have nuclei. It's for that reason that red blood cells don't have a long lifespan. Cells without nuclei cannot survive long term. So the average lifespan of a mature red blood cell is around 120 days. The old and or damaged red blood cells are constantly being taken out of circulation, mainly by the spleen, but the liver can also do that, while new ones are being made in the bone marrow. So hemoglobin then is that protein that is manufactured by red blood cells in their formative stages in red bone marrow. And when they come out of the bone marrow, they are chock full of hemoglobin. Okay. Hemoglobin is a complex protein. This is the diagrammatic structure of hemoglobin. It's basically 2 alpha and 2 beta sheets bound together with internal molecular bonds. So you have a globular complex protein. In the center, these loops here are the protein. These green discs here represent what's known as heme. And bound to the heme molecule are iron molecules. Fe is a symbol for iron. So oxygen molecules actually bind to the iron ion on heme in hemoglobin. That's the way it works. So have you heard of iron deficiency anemia, for example? All right, people who have iron deficiency anemia are deficient in iron and therefore are not able to bind as many oxygen molecules to their red blood cells as a normal person can.
So are they get tired?
Absolutely.
Because they're not getting the oxygen to the cells? Okay.
Fatigue easily, get tired, weak, lack of energy, so forth. Now notice that hemoglobin is contained only inside red blood cells. There is no hemoglobin dissolved in plasma. Normal. Okay? There are situations where when red blood cells rupture and lyse, their hemoglobin is released into plasma, but normally hemoglobin is contained in red blood cells. All but a very small amount of the oxygen is bound to hemoglobin. Less than 2% of oxygen is actually dissolved in plasma. So, hemoglobin. Now, the normal values for hemoglobin in adults are as you see here. These are some more values you need to know. In males, 13 to 18 grams per 100 milliliters. In females, 12 to 16. So you're always expressing things with a number and with units, aren't you? If we're doing total red blood cell count, it's so many millions per cubic millimeter, right? If we're doing hematocrit, it's a number with a percent, isn't it? All right? If we're doing hemoglobin, it's so many grams per 100 milliliters of blood, or serum, plasma, all right? So you can say grams percent if you want to. Grams percent is the same thing as grams per 100 milliliters. All right, now we talked about this before. Blood that's well saturated with oxygen, i.e. arterial blood, will have a bright red appearance because of the oxygen contained on the hemoglobin in the red blood cells. Blood in veins coming back to the heart has given up a considerable amount of its oxygen, but not all of it, and so it has a darker appearance. The brightness of the color of blood, or the darkness of it, is related to oxygen content. All right. Now, as that blood leaves the heart and goes to peripheral cells, tissues, and organs, does it lose any of its hemoglobin as it comes back to the heart? No. It's got the same hemoglobin it left with. It just has less oxygen bound to the hemoglobin molecules. All right, erythropoiesis is just a technical term for red blood cell production. Where does that happen? In the bone marrow. And where do we find bone marrow? Lots of different places, right? Sometimes physicians want to sample the bone marrow, don't they?
Don't remind me.
Pardon?
I said, don't remind me.
Yeah. And so, where are some readily accessible places that you can tap?
Spine.
Well, you would be sticking into a vertebra. I don't think so.
They usually do the
Hip,
The hip.
all right? The iliac crest is one place, right? Because you can feel your iliac crest right here. So, you know, the hematologist, the oncologist, put a little local anesthetic there, take a little number 11 blade and make a little nick, and stick a thing down there and poke through the cortex of the bone into the marrow, attach a syringe, and draw some out. But I think there's an even easier place to sample. Sternum. Because it's right there. You just have the patient lying supine, you know, strip it, drape it, put a little local anesthetic, a little puncture, and you just go. And you got a little trocar, pops right through, you draw the bone marrow out, and you're done. Now,
They're awake during that procedure?
oh yeah.
Okay.
Now, what kind of nutrients do you need to make red blood cells? Anything special? Well, you need the normal nutrients that all cells need. But for red blood cells, especially, we got to have iron, of course, right? And B12 is very important, also folic acid. Now, we'll stop on this, I think. This is the journey of a red blood cell. Here is the common stem cell, the hemocytoblast. And here we are progressing through the various stages. Now here we are getting close to coming out of the bone marrow. This is a normal blast. Notice that we're losing our nucleus right here. This is the stage right before they pop out. Sometimes when people are making a lot of red blood cells fast and pouring them out of the bone marrow, you will be able to see some of these reticulocytes on the scope. But most of the time what you're going to see coming out is this. No nucleus. All right, let me see what's next. All right, we'll leave this for next time because we're out of time.